So hello. So here this is the lecture 6. So in this lectures we are going to discuss the decoupled load flow methods. So basically decoupled Newton-Raphson load flow method which is there. So here we are going to apply some assumptions. So based on the assumptions, we are try to speed up of the computational efficiency as well as storage problem which is occurred in the Newton-Raphson methods. So in previous lectures we already discussed the and also taken the one example, that is the 4-bus system. Then we have to apply the Newton-Raphson load flow methods. So during calculation we can see the and we find there are two complexity problem. One is the computational efficiency, means computational time going too high, large. So means each iteration they are taking the same uh, computational time, as well we can say that the storage problems. So we are going to speed up the computational efficiency, as well we are going to solve the storage problem. This is our objective in this lecture. So here we are going to discuss the decoupled Newton load flow assumption, as we can see, which is already discussed. So we are going to apply few assumptions. So what are the assumptions? Only two assumptions are there. So we will discuss what are the assumptions. Based on these assumptions, we are going to solve the, or we are going to develop the decoupled Newton-Raphson load flow steps. And we have to take one example, that is the 4-bus system. So we have to apply these decoupled Newton-Raphson load flow method on 4-bus systems. So here you can see the decoupled load flow method. What are the assumptions? So you know that what are the problems of the Newton-Raphson load flow, which is already discussed. So as we can say that here we are going to discuss again it. So Jacobian is calculated and triangularized in each iteration in order to obtain the LU factors. So each iterations we have to calculate the Jacobian matrix, and we have to uh, calculate the correction factors in system. So to speed up the overall solution process, and Jacobian will be often recalculated only after few iterations. So here, if we want to increase the speed of the overall solutions, so we have to use the Jacobian matrix in such a way that if certain values are going to vary, then we have to calculate the Jacobian matrix again. Otherwise, we can use past iteration values. So in such a way, we can increase the speed of the overall computational time. So that is the main objective of the decoupled load flow method. So when solving the large-scale power transmission systems, an alternative strategy for improving the computational efficiency and reducing computational storage requirement is developed and known as the decoupled power. So what are the assumptions? So principle underlying the coupled approach is based on two observations, that is two assumptions. First is the change in the voltage angle at any bus principally or primarily affect only the flow of the real power in the transmission line connected to that bus, and there is low, we can say that negligible effect on the reactive power. So this reactive power is going to unchanged. So we can say that the del or voltage angle variation reflect in terms of the real power flow. So this is the first assumption. Second assumption, change in the magnitude voltage at any bus primarily affect on the flow of reactive power flow in transmission lines. And there is no effect, or we can say there is negligible effect on the real power. So generally we can consider this is the unchanged. So using these assumptions, you can see the voltage, it depends on the reactive power, and angle, it depends on the active power. So using these two assumptions, we can decouple. So as you know that in Newton-Raphson load flow solutions, we can solve the voltage angle correction factor as well as voltage magnitude correction factor simultaneously. So using these two assumptions, we can decouple these two correction factors. We can solve these two correction factors separately. So that's why it is called a decoupled load flow method. And using decoupled approach, we can speed up the overall computational efficiency as well as we can reduce storage problem in the Newton-Raphson. So here we have to just again going to apply these two assumptions on the Newton-Raphson method. So first assumption is that the partial derivative of the active power with respect to angles is much larger at a particular bus and much larger than partial derivative of the reactive power with respect to angle. So we have to just consider it is approximately 0. So only we are going to consider the voltage angle depends on the active powers. If we are differentiating, if voltage angles is going to change, then it reflects in terms of the real power change. So it's not going to change the reactive power. So with reactive power change, we are considering that it is a constant value. Second observation, reactive power change with respect to magnitude voltage is much larger than the real power change with respect to magnitude voltage. So here also we are going to consider that it is 0. So means reactive power change with respect to magnitude voltage we can consider it is a 0. So it is independent. So only if any bus have the magnitude voltage is going to change, so we have to calculate only the reactive power voltage. So reactive power will be changed with changing the magnitude voltage, and active power change will change the voltage angle. So we can apply on the Jacobian matrix, then we can see that the matrices J12 and J21 becomes 0 because these two matrices differentiate reactive power with respect to del and active power with respect to magnitude. So we can see that when we are applying these two assumptions, we can get the J12 and J21 becomes 0. Only J11 and J22 will be there. So these two sub-Jacobian matrix elements are going to 0. Then after the application of the after the calculation of these two assumptions, we can get these two equations. So first equation you can see this one. First equation, this is the J11 matrix and this is the correction factor in terms of the voltage angle. This is the mismatch power in terms of the active. We have to calculate the mismatch power same as the we already discussed in the Newton-Raphson load flow method. And after that we have to partial derivative or we can say that you have to calculate J11 using partial derivative approach. So here active power at bus number, this is the example they have given for the bus number 4. 4 bus system. So in 4 bus systems we have taken the bus number 1 is the slack bus number 4 is the PV bus, and bus number 2 and 3 are the load bus. So there are 5 variables are unknown. So that is the del 2, del 3 and del 4. And we can see that magnitude voltage V2 and magnitude voltage V3. So these are the 5 are unknown. So order of the J11 will be 3 by 3. So we have to calculate the J11 using the partial derivative with respect to del 2, del 3 and del 4. Then we have to put the all initial values, means voltages and angle, to calculate each elements, means diagonal elements of the J11 as well as off diagonal elements of the J11. Then further we have to calculate the del 2. Similarly, we have to calculate the J22. Here we have to calculate the reactive power partial derivative with respect to magnitude voltage. So So all initial values we have to put and calculate the mismatch power, reactive power, then calculate the value. So here you can see these two equations, correction factor in del and correction factor in magnitude voltage, both are independent during the calculations. They are decoupled. So that's why it is called a decoupled. We can calculate first voltage angle corrections or magnitude voltage corrections. So we can give the preference. So based on our objective, we can calculate which one is the more dominant. So based on our objective, we can calculate. So these calculation, in terms of the calculation process, these two equations are independent. But when we are calculating the particular higher bus active power and reactive power using the mismatch power calculations, you can see the power equations are depends on the magnitude voltage as well angles. They are not independent, but during the when we are going to calculate the correction factors, we can see that these are the independent to each other. So here the decoupled load flow method, you know that the decoupled in the sense that the voltage angle correction, they are calculated using only the real power mismatch, and voltage magnitude are calculated using only the reactive power mismatch. So they are just using this one. But we can say that the coefficient matrices J11 and J12 are still dependent on the active means magnitude voltage as well as the voltage angles. When we are going to calculate our partial derivative with respect to the voltage angle or voltage magnitude, we can see the active power and reactive power depends on the these. So only the calculations means in the sense of the voltage angle correction factors means del as well as magnitude voltage calculation values are independent to each other. So we can generalize or we can solve these equations based on the requirements. You can see that this is the first equation. Here in the first equation, we have to first calculate the mismatch power. Using this mismatch power, same process we have to apply as discussed in the Newton-Raphson method. Then we have to apply the J11 means Jacobian matrix J1 we have to calculate means active power are differentiated with respect to voltage angles and put all the initial values. We have to calculate each elements in terms of the numeric value. Then we have to calculate del 2, del 3, del 4. This is the correction factor in voltage angle. Then we have to update these values. So this is the updated values. Then this updated value we can use in the calculation of the reactive power mismatch. So remember that this updated values we have to use in calculation of the reactive power mismatch. So reactive power Q2 and Q3, Q4 we have to calculate it. Then further we have to calculate the elements of the matrix J22, which is the means reactive power differentiated with respect to magnitude voltage, that is V2 and V3. So we have to calculate the V2 and V3, then update this one. If this voltage values are lies within the tolerance limit, then we can terminate, otherwise go for the next step. So here we have to going to discuss the or we are going to formulate the basic algorithm steps of the decoupled load flow. So first we have to same process we have to apply as a Newton-Raphson method, but a little modifications are there. So we have to first get all the initial values of the voltage angle and magnitude. Then we have to use to calculate the mismatch active power. Only we have to calculate the first active power mismatch. Then we have to calculate the Jacobian matrix as given in the equation 1. Then after that calculation of the J112 and active power mismatch, we have to calculate the voltage angle correction factor. Then we have to update it. So this updated voltage angle values is used in the calculation of the mismatch power in the reactive power as well as J22. So using equation 2, we have to calculate the correction factor in voltage magnitude, and for after that the calculation we have to update. So this is the update equations. Using update we can multiply. If these correction factors are lying within the tolerance limit, then we can terminate, otherwise we go for the next step. So in the next step we have to use the updated voltage angle as well as magnitude voltage. This is the basic steps of the decoupled load flow. Then here we are just going to take the example. Here I consider the same example as it is in the taken in the international network. So here four bus system. As you know that the bus number 1 is the flat bus and bus number 4 is the PV bus. Bus number 2 and 3 are the load bus. So all the types of buses and per unit voltages, what are the condition of the active power, reactive power are given in the bus data table, and this is the line data. So using line data table, so you can calculate the admittance matrix. I'm going to discuss how to calculate the admittance matrix. Is already discussed in the previous lecture. So here we are going to apply the decoupled load flow method on 4 buses. So before we are just choose the initial value. So here the initial value at the bus number 2, this is the here bus number 2, the voltage magnitude and angle, and voltage angle and magnitude voltage and angle on bus number 2, and bus number 4, this is the PV bus. Here we have to achieve the voltage. Means total twice quantity we have to calculate. Then what is the order of the J112? So you know that the J112 is depends on the voltage angle. So here voltage angle at bus number 2, voltage angle at the bus number 3, and voltage angle at bus number 4. So del 2, del 3, del 4 we have to calculate. So here three quantities are unknown. So order of the J22 is always requirement. So we have to calculate this J11, that is the 3 by 3. So 3 rows and 3 columns. And order of the JPP depends on the reactive power mismatch power as well as the voltage. So it depends on the only the load buses. So only two buses are there, load buses are there in the system. So bus number 2 and 3 are the load buses. We have to calculate magnitude voltage as bus V2 and magnitude voltage as bus number 2 means V2 and V3. So order of the JPP is the 3 by 2. At bus number 4, the magnitude voltage is given data, so it is known. So we are not going to calculate. Only V2 and V3 we have to calculate. Then we have to apply. So we have taken all the initial rates, and we have also calculated the what is the order of the behavior matrix J1 and J2. Then here we have to first calculate the mismatch power. So mismatch power, we know that the mismatch power we can write del P is equal to for the any bus. Suppose we are consider the ith bus, del Pi is equal to, that is the PGI means that is the generated power at the bus I, and then minus PDI, which is the active power demand at the bus I, then minus PI calculated, which is the we have to calculate. So PI calculated. So PG and PDI we can get these values and convert these values in terms of the per unit. Here the reference value 100 MVA and 230 kilovolt. So we have to convert it into the per unit and put the PGI and PDI value, and PI we have to calculate using these equations. So here del theta I, del n, del I, gi, all these values are taken from the line data as well as so these values we have to put here, calculate the PI, PDI, TDI for the bus number 2, bus number 3, bus number 4. So we already calculate the mismatch. So you can see this is the mismatch power at the load buses we are getting the mismatch. Because at the load buses there is no generation. So PGI will be 0. So when all these values we are getting, that is the negative. This will be 0. So at the bus number 2 and 3. So but bus number 4 there is a generation, there is a breakdown. So we are getting the a positive mismatch. Then now come to the calculation of the J11. This is the J11 matrix. So this J11 we can calculate using the partial derivative of this active power with respect to angles. What are the angles? That is the del 2, del 3 and del 4. So here I, when we are putting I equal to 2 in this equation, so this becomes P2. Here in RHS side we can also put the I equal to 2. Then differentiate this P2 with respect to del 2, del 3 and del 4. So other quantity we are taking as a partial. So here we are taking the partial derivative and put all the initial values of the admittance, voltage angle and magnetic angle. So we can calculate. So this partial derivative with respect to P2 with respect to del 2. This is the partial derivative of the P2 with respect to del 3. This is the partial derivative of with respect to del 4. So same process we can apply here the active power injection at bus number 3, that is P3. We have to put here I equal to 3 and derivate and put all the values calculate. So here also we have to put I equal to 4 and differentiate this P4 with respect to del 2, this can with respect to del 3, with respect to del 4. So finally we have to calculate this voltage angle correction factor del 2, del 3, del 4 at bus number 2, 3 and 4. So we are getting this equation. These are the equations. So then we have to update what are the values of the del 2, del 3, del 4 using this correction factor. Then finally, so next step we have to again calculate the what are the magnitude voltage mismatch. So it depends on the only the reactive power. First we have to calculate the reactive power mismatch. So reactive power mismatch we have to only calculate using the mismatch condition, means del Qi equal to del Pgi minus sorry del Qi equal to Qgi minus Qdi minus Qi. So what are the reactive power generation at particular bus I, and what are the reactive power demand and calculated value. Calculated value we can calculate using this. Same process we can apply here. So here updated value, we are going to use the del 2, del 3, del 4, these should be updated value. It is already calculated in the previous slide. So these values we are going to use here. But the magnitude voltage we have to take as the initial value. So we have to calculate this value. So suppose they have given here, they are differentiating with respect to del Q2 by del V3. So we are getting this much equation. So we can put, so here del 2, del 3, del 4, all these are we have to take as the updated value. So we are getting to finally this value. And we have to again calculate the del Q3 by del mod V3. So we are differentiating this the equations with respect to the magnitude voltage at bus 3. So keeping other values as the constant, and we have to apply the partial derivative and put all the values. So we are getting this is the final. So this numerical value we can put. Finally, we have to put in these equations. So these terms we are getting the 0 because there is no connection between the 2 to 3 and 3 to 2. So there is no flow of the power in direct power. So only diagonal units we are getting. So this is the reactive power mismatch which is already calculated. Then we can calculate this mismatch power. So we are getting the mismatch power. This is the at bus number 2. This is at bus number 4. Then we can update the voltages at bus number 2 and 3 and check the correlation. If we are getting the light within the correlation, then we go terminate that. This is the final solution. Otherwise, we for the next step. So this is all about the decoupled load flow model. This is a very simple comparative method. They are going to step. So in this problem, we can see that what are
storing that. So here J12 and J2 become 0. There is no space. Only J11 and J22 will have to replace. And computational time is also going to increase. So using decoupled method, we can enhance the computational efficiency as well as computational time and space problem. So we already discussed and I have applied this load flow decoupled method on a 4-bus system. So this is all about the decoupled load flow system. Thank you.